Sharing my screen, not on mute. Might be a good start. So sad. It's our last financial math section that we're going to do. You've reached the final level that we'll do. So I guess we could do a recap. Wow. Let's bump this down. And I'm going to steal from the recap so I don't have to memorize it all. How can I, oops. Oh, no. Copy. Because we need all this stuff. Hey, what the heck? Fine. I don't know why it's being so difficult. Oops. We're kind of done with the simple interest, but we did move on to compound interest and annuities where we make regular payments, right? Those are going to be our go-to players. And let me finish copying there. Copy. Paste. So if we have an annuity, right, then we have regular payments of amount M, right? And then last day, we built this up and we said, okay, well, I could either make payments, right? And let's say you buy a car, right? And you're making payments on this car for, let's say, 5 years, pretty typical. And the alternative is that you pay cash, right? And so depending on what the dealership wants, they might have some benefits, but there is some present value of those payments that you're making, right? So then we said, okay, well, that present value is going to be, hey, erase my P, is going to be this principal amount, right? Where we let A be the same thing, right? And so we let all these payments grow until they reach an accumulated amount, and then we bring it all back to the principal amount. And regardless of how you got there from a fixed lump sum versus regular payments, right, they have to be equivalent. Okay? And then, so how we did that was just shouldn't say just, was setting these two equations equal to each other, right? And we can either solve for, okay, well, what lump sum is the equivalent of these M's, right? Or what payments would be equivalent to this principal amount, right? And we just move between the two. So you know what? No. Let me have a reverse sneeze first. And then Felix was in our office all day, and I'm sadly allergic, and I don't touch him, but I know he's so cute. But now I'm all sneezy. All right. I won't include it in the review because the formula that we were working with last day is just down here, right? And so we were working between the P and the M, and those were only two options that we could solve for, right? And so as a refresher, because it's been nearly a week, A is the accumulated amount, right? So if you let it grow, then you reach this accumulated amount. P is the principal amount, right? Either invested or what you borrowed, right? Depends on the situation, but they behave the same, right? R is the interest rate per year. T is the time in years. N is the number of compoundings per year. And in this course, it will also be the number of payments per year. You can level up just slightly beyond what we're going to do in this course, and you can have kind of different payment frequencies from your compounding frequencies, but all you need to do is adjust your rate, right, to match it. And so you can easily get there, but we won't have to. And then M is the amount of each periodic payment. Okay. Oh, fine. Just because they're not exactly the same. They have the same formula. And so we also saw that P times 1 plus R over N to the N times T can be equal to M times 1 plus R over N to the NT minus 1. I'm going to need to confirm this. Divided by R over N. Did I miss anything? M1 plus R over N to the T minus 1 R over N. Nice. We forced these two A's to be the same, right? And then we can move between a lump sum and payment amounts, right? Or regular payments. And so what this looked like, now I've really done it. Hey, I keep thinking of stuff to add. It's bad. If we visualize this, right, and it might be helpful to draw a timeline. If you find it helpful, that's great, but it's not something I'm expecting you to do because a lot of our problems don't really require it. Until today, maybe they'll be a little bit more helpful. But if we imagine kind of today, right, we go out and we buy a car or a house or something fun, and we have to pay it off, let's say in 5 years from now. So then we make these regular payments, let's say monthly payments, 5 years is 60 months. Let's say monthly payments. So 5 years or 60 months, making this the 59-month mark, 1 month mark, 2 month mark, 3 month mark, okay, and so on and so forth. I make some payment amount M each month for 5 years. And what we said was, okay, these guys are all going to be worth some amount P today. And so that's how we're able to say, okay, well, this P, right, here is equivalent to M made for 5 years. Because the bank doesn't care, right? You've committed to paying these M payments, right? Or M payment amounts for 60 payments, right? And so if you say, hey, I want to pull the trigger and I want to pay it all back, right, which is what we're kind of building towards today, or among other things, but then there's some value that you've committed to paying, right? And so if you pay off a loan early, right, we don't pull it back to today because that would just be paying in cash, right? But if we did kind of have an alternate scenario, alternatively, what if we're here today, we've gathered here today, and you've committed to paying for 60 months, right? But then, unbeknownst to you, right? 1 month, 2 months, 3 months, maybe 1 year later, you win big. Whee! It's a party. These are stars. Wow, you win the lottery. And you say, you know what? No. Sure, I've made all these payments, but now I'm going to pay this off. How much do I owe you? Right? And so what we're going to need to figure out is, well, how much do you owe? Right? You have still committed to paying M dollars per month for a remaining number of months, right? 60 minus 12 months, probably, right? And so you've already committed to paying that, right? And so the bank says, all right, well, you know, you already paid these. These are all done, right? But now what we want to do is we want to take these amounts and they'll be worth some amount P. This looks the same to me, right? It's just a little bit longer, or I guess the first one's a little bit longer because it's the entire period of time, right? And so what we can do is we can think of this as kind of the where P is the cash value of the remaining M payments, or of the remaining payments. I'm missing a word. Of the remaining payments. So we can ignore these guys here. We've already paid these down, right? And so, okay, what if we just ignore them then, right? And what if we just treat the 12-month mark, right, which is a year into my 5 years, right? And so now this is going to have a length of 4 years, right? But that's okay, right? Here, the length of this, oops. The length of, or the number of payments was over 5 years, right? And we know how to solve that from last day. And so now all we're doing is we're shortening this a little bit, right? And taking into account just how many payments were remaining, right? That I already committed to have to pay them, right? But it doesn't matter if you pay it as just a lump sum or as these payments. So that is miscellaneous, I guess. Miscellaneous. There's a couple of different options, but that's where we're going to start with these. What a terrible name for a section. Miscellaneous application problems. It's true, but wow. So now I'll skip the preamble because I already did it, but I'll highlight this. To find the outstanding balance of a loan at a specified time, we need to find the present value P of all the future payments that have not yet been paid. In this case, T does not represent the entire term of the loan, right? It represents the remainder of the loan, right? Those payments that you've made, they're all behind you, so you can kind of ignore them, or at least that's how I think of it in my mind. So T now is going to represent the time that still remains on the loan, right? Besides that, nothing's really changing, right? And so N times T represents the total number of future payments, right, that you had originally committed to. Blow this up a little bit. So if a loan has a payment of M dollars made N times a year at an interest rate R, then the outstanding value of the loan, blah, 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 P, so is given by P. And we use this exact same formula, right? Except now the change is that T is the amount of time still remaining in the future. This could involve having to figure out what T is, right? And so we already saw that, and it's not, it's not terrible, right? If I say, okay, one year after you took out this loan, you win the lottery, party time, and you say, I'm gonna ditch all this debt that I have. Or you could invest it if the interest rate is better. Oh, options. Luckily, you know how to compare the two now. Okay. So let's see here. Kind of a typical, whoa, I don't know what that was or how I did that, to be honest. Here we go. Typical scenario. Well, maybe not. Mr. Jackson bought his house in 1995. Wouldn't that be nice? And financed the loan for 30 years. Well, they had insane interest rates though. So, yeah. And financed the loan for 30 years at an interest rate of 7.8%. His monthly payment was $1,260. In 2015, Mr. Jackson decides to pay off the loan. Find the balance of the loan he still owes. Yeah. Now, I do find it helpful to kind of map it out with this timeline, right? Just so we can kind of catch our bearings, but you don't have to, but I'll do it so that you can see it. So in 1995, he bought a beautiful home with a chimney and everything, maybe a yard. Then he committed to paying it off over 30 years. He was making monthly payments. And so for 30 years, that makes 360 months. Now, I also, because I read the question, I know that in 2015, right? So 1995, let's do 1995 plus 30 years. Hey, that's now 2025. But at some point here in 2015, he decides, scrap it. I'm just going to pay this off. So here at 1 month, 2 months, blah, 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 blah. 2015, he's been paying it off for 20 years. Holy smokes. Crazy. So 20 years times 12 is 240 months. And he was paying 1,260, 1,260, 1,260, 1,260. That was his last monthly payment. But he did commit to paying 241 months, blah, 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 blah. all those payments for another 10 years. So how I indicate that we're trying to group these all together is I use that curly bracket and I draw an arrow back to the date that I want to find the principal value of this thing. So I'm trying to solve for P. And to do that, we need to know how long, how many groupings basically we have. The easiest way to do that is just to find T, right? Because we know N is 12, right? He's making monthly payments. So then we can do that math. Otherwise, N times T would be 360 minus 240, right? But we can just stick to the script and say, okay, between 2015 and 2025, there are 10 years. He's committed to making monthly payments of $1,260 for 10 years. So we need the rate. I'll just jot it down here somewhere. The rate is 0.078. And we need the compounding frequency or the payment frequency, because they'll be the same, is 12 times per year. And I'll just make a note of it here, 1260. You could also use this to figure out how much he paid for his house. If you pulled it all the way back. Okie dokie. So we're trying to solve for this P. The only adjustment from last week is that we need to change the length of time, but now we're ready. We're ready. Move this over here. Okay. P times 1 plus R over N to the N times T is M times 1 plus R over N to the N times T minus 1 divided by R over N. I've got all these components except for P, and that's the way I like it. 1 plus 0.078 divided by 12. 12 times 10 years. Because that's the only change. 1260 times 1 plus 0.078 divided by 12. 12 times 10 minus 1. 0.078 divided by 12. I'll do this chunk first and jot it down. And then I can use that same information and subtract 1 and multiply by M and then divide by 0.078 divided by 12, right? And so that's how I'm going to do it. But as long as you land on the same answer, that's great. Is it 1 plus? Yeah. Store this. 2795734. I really hope I did it. I didn't flip it.
Yep.
That is a huge relief. You need to pay $104,761.34 after 20 years, 1995. Uh-huh.
I know.
I know, right? Don't worry. We're gonna build an amortization schedule. Don't you worry. Now, the reason this section is miscellaneous is because it's not introducing any new formulas per se, but we are using the formulas that we do know and potentially combining them, right? And so one of those kind of types of scenarios is up next. You won't believe what happens next. I like that they have to give her a name. Suppose a baby, Aisha, is born and her grandparents invest $8,000 in a college fund. Come, nice, right? The money remains invested for 18 years until Aisha enters college, and then is withdrawn in equal semi-annual payments over the 4 years that Aisha expects to attend college. Should probably make that 5, but that's okay. The college investment fund earns 5% interest compounded semi-annually. How much money can Aisha withdraw from the account every 6 months while she's in college? There's a brain teaser, right? What happened? You had to map out the kind of the timeline of this money, right? They went to the bank and they deposited $8,000. And then it sat there growing for 18 years, right? And then that sounds like just compound interest to me, right? So then that accumulated amount turns into the principal amount for these regular payments, right? And then we're going to partial them out over these semi-annual payments over the next 4 years, right? And so I do find that it's helpful to draw this timeline, so I will. Aisha is born. And her grandparents, they say, wait a second, we're going to the bank. It's gonna sit there. I guess I didn't need to draw the length of the timeline proportionately, but it's gonna sit there for 18 years. Right? And so phase 1 is, okay, this is going to grow to some accumulated amount. And here, I'll call this P, right? That's your principal investment. And then we have these, you know what? Get a little bit longer. You can do it 18 plus 4 years, or remember, this is just to help you visualize what's going on. So if it makes more sense for you to say this is the 4-year mark, that's fine. I get it, right? In fact, that's kind of how my mind works, right? Because then we can just kind of zero out time here, right? Technically, it's 18 plus 4 years later, which is what, 22? Let me confirm. So 22 years, right? But 4 years of payments. 4 years. Can I use a lowercase m? 4 years of payments. So she's going to make, or she's going to withdraw equal semi-annual payments every 6 months. So in 4 years, that's 8 payments, right? 1, 2, 3, 4, 5, 6, 7, 8. Yeah, not bad. And I'm only drawing out all these M's because there aren't that many, right? And it's easier to visualize them. So now, these payments, right, they're coming from some principal value, right? So we're starting with some amount, and then we're taking out M's until we end up with 0, right? So our accumulated amount becomes 0. So that's kind of pointless to us, right? But if we think of these payments, they're going to have some principal value, right? And the key is that that principal value has to be the same as this accumulated amount. Right? So it's kind of like passing the baton, right? So we let it sit there and it grows to some accumulated amount, and then that becomes the principal amount for these regular payments, right? And this is the same as what we were doing last week and what we started with today, right? Just figuring out, okay, what are these regular payments worth, right? If I just have a lump sum, right? Or if I'm drawing from a lump sum. Okay. Things to look out for is in this scenario, we just have the one interest rate. But it's pretty common for these problems to have one interest rate for the first part and then a different interest rate for the second part. So just something to keep an eye out for, right? And so let's see what we've got here. Her grandparents invest $8,000. I thought for a second it was 80,000. No, it's 8,000. In a college fund. The money remains invested for 18 years. And so for this section, T is 18. And the rate is 0.05, compounded semi-annually. Right? And so N is 2 times per year. So step 1 is going to be to figure out, okay, well, what's this $8,000 going to grow into? Right? An alternative question, right? We can move the other way, right? What if I, when I retire, I say to myself, hey, you know what? I need $2,000 a month or something like that. Then you force these M's, and then that has to last you for some amount of time, right? Kind of gruesome, but 20 years, let's say, I don't know. And then you're all out of money, I guess. And then you can force that to be the accumulated amount, and then how much would I need to invest today, right? That kind of thing. And so you'll be able to kind of construct these problems using the formulas that we've already kind of established. Okay, so in this scenario though, we're taking this 8,000 and we're growing it. So let's figure out what this A is. A is P times 1 plus R over N to the N times T, right? No regular payments. If we had regular payments, then yeah, we would need to take those into account with that bigger formula. But here it's just sitting there. So 8,000 times 1 plus 0.05 over 2 and 2 times 18. Let's see what we get here. 0.05 divided by 2 plus 1 to the power of 2 times 18 times 8,000. Whoo! I guess I shouldn't do the dollar sign yet. 19460.28253. Look at how generous Aisha's grandparents are. $19,460. Oh, 28. This becomes the principal amount in phase 2, let's call it. I think of it as phases. Now, the amount of time for phase 2 is just 4 years. Right? So T is 4, and the rate is the same, but I'll just jot it down. And we're making semi-annual payments, and luckily the interest is compounded semi-annually. It will be. 2. So now I know that my P has to be $19,460.28. Right? Otherwise, it's not going to work. Or maybe I should say this becomes our P. Right? In P times 1 plus R over N to the N times T is equal to M times 1 plus R over N to the N times T minus 1 over R over N. If a formula can be a run-on sentence, this is it. So now, we use that as our P, and we want to solve for M. What amounts will she be able to get every 6 months to help pay for school? Let's see. Making sure you switch your T to 4 years, right? For this phase 2. Right. And simplify this side, simplify this side, solve for M, just like last day. I say that. Here we go. 1 to the power of 8. Oh my gosh. Every 6 months, she can get $2,714.07. Nice. Hard part of these is not really the math anymore, right? It's figuring out, okay, well, what do I need to do here, right? That's, I would say, the hardest part now. So here's another one. We're watching Aisha grow up, isn't it so nice? Well, first, did you guys get the 2,714? I thought you were beating me. That's why I had to pick up the pace.
Counted them all.
Gotta catch them all. Oh, I need more jokes. I know. I'll have to make it like a bonus on the test or something if you can tell me a Pokemon joke. Ooh. Because I only have the 2. Which I've already told. Ready for another one?
Oh, keep going.
Oh, she graduates college.
Aisha graduates college and starts a job.
Wow.
Wow. She saves $1,000 each quarter, okay, depositing it into a retirement savings account. How responsible. Suppose that Aisha saves for 30 years and then retires. So now what's the scenario? She's making payments, and they're going to grow, right? And be worth something at the end of 30 years. At retirement, she wants to withdraw money as an annuity that pays a constant amount every month for 25 years, right? So she's determined, okay, for 25 years and then the end, I guess, or you're poor. During the savings phase, hopefully she has other income. During the savings phase, the retirement account earns 6% interest compounded quarterly. But during the annuity payout phase, the retirement account earns 4.8% interest compounded monthly. So we have to keep track of those 2 rates, just like I warned you about this. Calculate Aisha's monthly retirement annuity payout. This is only slightly different from the previous question, right? How is it different? Instead of having this lump sum here, right? Now we're making regular payments, and they are going to be worth some accumulated amount, right? And then we want to figure out, okay, well, what amount can we get for 25 years, right? And I think it's monthly or something like that. I think this warrants a fresh page. It's a big problem. So it doesn't have to be beautiful, but I do recommend mapping it out. Right, kind of sketching out the scenario, and that's a way to organize the information that you're getting as well, right? So, and like I said, it doesn't have to be that great, but she graduates. How can I draw a graduation cap? Here she is. Free. Looks something like that with tassels. Looks like she got her doctorate. She graduates. And then she works for 30 years. Making quarterly payments, quarterly payments for all those 30 years. Then phase 2, now she's on a beach somewhere in the sun, and there's water, and it's beautiful. I know, right? This length of time is 25 years, but on this timeline, all right, let's say this is 0 years, that puts us at 55 years. Whatever you find is more helpful, it doesn't really matter. Right? Okay, so we know that she's going to be making payments, and usually what I do is I do the first 2 and then the second to last one, and I just kind of join them with dots like this, right? Just to indicate that, okay, it keeps going. I don't want to draw out all these individual payments. They all behave the same. And they happen every quarter. Thank you. For 30 years, which makes 120 quarters. Right, 4 times per year for 30 years. So first quarter, second quarter, 119th quarter, and then she retires. The value when she graduates of this thing is 0, right? She hasn't deposited anything, right? She's not starting with anything. And so, right, these, what color should I do for phase 1? Guess I can do the same. Oops. Should include that last 1,000. These are going to grow to some accumulated amount. This $1,000 has been sitting there compounding 119 times. It's going to be a lot bigger than this last one, right? A lot. Might be a stretch, but the accumulated amount takes that into account. And then let's see here. What do we need? We need T. T is 30 years for that first stretch of time. And we're making payments at n equals 4 times per year, and it's also compounding quarterly, so that's nice. In fact, it is earning 6% compounded quarterly. And of course, we know our M is 1,000 for this section. Now, the next 25 years, she wants a constant amount every month. So now we have changed it to monthly payments. And so we can think of it as kind of 1 month into retirement, 2 months into retirement, and then for 25 years, 25 times 12 is 300 months. And she's going to get some amount M that we need to solve for. That amount M is being dispersed from that A that she's been saving. So we do the same thing, right? This A gets handed over and it turns into a P for this kind of new phase of our monies. Switch to light blue because the orange was kind of hard to see. T is 25 years. N, in this case, is 12 times per year. The rate, right, this is where we need to keep track of the different rates and the different compoundings, right? And so the rate is 0.048. And that's all we need. And then we're trying to solve for M. So step 1, find A. And then we have a jumping off point for P, and then we can solve for M. I'll write a note, solve for M. Okay. A. Do you remember? So you're choosing between 2 A formulas. Let's go way back here to our review. Either compound interest, but compound interest was when we started with some amount and it just sits there, right? Compounding every now and then, right? Growing a little bit. Whereas whenever we have regular payments, then we have an annuity, right? And so then we need to use this formula here, right? To take into account the regular payments. Unless you want to do them all by hand, then each of your M could be your P and you'd have to pull them all forward and add them all up. But I would rather just use this formula, which does the same thing. So, right, there's nothing wrong with using each of these 1,000 as P's and pulling them forward for their length of time, but you'd have to do it 120 times. And I say, no thanks. So this is what this formula does. M times 1 plus R over N to the N times T minus 1 over R over N. Okay. 1,000 times 1 plus 0.06 over 4, making sure you keep track of your rates and your compoundings, right? They're separate and different this time. Okay. And that's why I think it's nice to kind of separate them up here. 4 times 30 minus 1 0.06 over 4. All right, here we go. 0.06 divided by 4 plus 1 to the power of 4 times 30 minus 1 times 1,000 divided by 0.06. divided by 4. Same. Nice. Notice how I round to 2 decimal places just because money only goes to 2 decimal places. And so when you go to the bank, you can't bring 0.1915 pennies. You only get to bring 19. They'll only give you 19. But looks pretty good. She has 331,288 and 19 pennies after 30 years, I guess, but still pretty good. From paying $1,000 every quarter. Now, this amount is going to sustain these regular payments for 25 years, right? And we need to figure out, okay, well, how much can that possibly be? Well, let's see here. T is 25 years, N is 12, R is 0.048, right? So our N and our R have changed, right? So I only mention that because sometimes I'll store my R over N, but then I forget that I stored the wrong one. So just keep track of those. Okay. So now this becomes P in her retirement fund. Okay. P times 1 plus R over N to the N times T. Nope, I don't know why I did that. Is M times 1 plus R over N to the N times T minus 1 over R over N. Right, and so here. And we want to solve for M. Okay. 331,288.19 times 1 plus 0.048 over 12. Let me just confirm. 0.048 divided by 12, yeah. 12 times 25 years. It's over. Trying to stack my equal signs, but it's hard. And solve for M. One plus 0.048 divided by 12. 12 times 25 minus 1 over 0.048. 12. Okay. 0.048. Whoa, Emily. I tried to forget a zero, making it 48%, and that would be insane. So good thing I caught it. she's gonna get monthly payments of 1,898 and 27 pennies. Not bad for making $1,000 payments every 3 months for 30 years. And then she can get 1,898 per month for 25 years. It's nice. Well, I guess I should check in. How you guys got? No pressure. Some pressure. Nice. That confirms it enough for me, I think. So the last part, which is crazy, okay, but that's okay. More time to work on your problems. Right? Last part of miscellaneous is an amortization schedule for a loan. And so an amortization schedule, if you have a mortgage, you can usually see your amortization schedule, and all it's doing is it's outlining how much of your payment, right, is paying off the principal versus paying off the interest, right? And so what we can do is we can break down each payment. So every month, usually we pay mortgages monthly or car loans or whatever. You pay the same amount, right? Every month, let's say, or every week or whatever you decide to do. Okay. But as you pay more and more off of your loan, right, you're only charged interest on the amount that's left owing. Right. And so at the end of each month, you owe a little bit less and a little bit less. And so then you're deducting or kind of reducing the amount that you have to pay interest on. So that's nice. Right. And so an amortization schedule is a table that lists all payments on a loan. It splits them into the portion devoted to interest because the bank says, no, you committed to paying this interest. Right, and then whatever's left over will go towards paying off your loan. Okay, so they take their interest portion first, and then another portion or the remainder is applied to repay the principal of the loan, right? The initial amount that you borrowed. Okay? And then it calculates the outstanding balance on the loan after each payment is made. And so this is where there are some kind of devastating instances where, house prices just drop like crazy and people are paying more than their house is worth and things like that. And what's it going to cost you to get out of it? All right. Terrible. As a baby example, and of course you can scale this up to a car loan or a mortgage, but if we think about even monthly payments for 5 years, okay, 5 times 12 is still 60, right? So then what we would do, because we're going to look at each individual payment, you would have 60 lines of math, and that sounds terrible. Right, and so of course you'd use Excel to do that probably a little bit quicker. And so for a mini version, we're gonna say that we borrowed $500, and we borrowed it for 6 months. So cute. at a rate of 12%. We're going to make an amortization schedule showing the monthly payment, the monthly interest on the outstanding balance, the portion of the payment contributing towards reducing the debt, and the outstanding balance. We usually also list the payment number, right? Just to make sure that you've got all the payments that you need to list. I'm going to make this a little bit bigger. Yeah. And so a typical amortization schedule has all these columns. Yeah. Now, there's a little bit of work that we need to do, right, before we can start filling in this list. Yeah. Because we know we borrowed $500, and for 6 months, we're going to make monthly payments. Okay. Which means how many payments? We're going to make 6 payments, right? 1, 2, 3, 4, 5, 6. But also, we need to figure out what the payment amount should be, right? And so before we can start here, before we build the table, we need to find the payment amount. The payment amount, we borrowed $500, and that's the principal, right? And so we can say P times 1 plus R over N to the N times T is M times 1 plus R over N to the N times T minus 1 over R over N. So we have our principal amount of $500, and we need to figure out what the payment M is. Oops, P, wait, was 500 times 1 plus 0.12 over 12, right? Monthly payments. And 12 payments per year, but only for half a year, right, or 0.5. And maybe to keep with the fractions, right, 6/12 of a year, but that is half a year, right? Which means 6 payments. It's going to be M times 1 plus 0.12 over 12 to the power of 12 times 6 over 12 minus 1 over 0.12 over 12. Hmm. 0.12 over 12 plus 1 to the power of 12 times 6 divided by 12 times 500. Oh, now I've done it. Because I lost it. I have to do it again. 0.12. And I didn't save it. Let's store this in a. Keep blurring my words. Hopefully that's not a problem. 0.12 divided by 12 plus 1. I'm just going to do to the power of 6 minus 1 divided by 0.12 divided by 12. 6.15201506. So your monthly payments is $86.27. That's going to be the same for all 6 payments, right? And let's do payment number 1, 2, 3, 4, 5, 6. All of these payments have to be the same, right? And there are ways that we can make adjustments for the last payment, but let's just ignore that. And 86.27, 86.27. We did all that work, so why not jot it down? Right? Each month you pay the same amount. But what we're going to see is that in the beginning, a lot of it goes towards paying, or not a lot, but some of it is going towards the paying off the interest, right? But as we move through our payments and reduce the amount owing, then we need to pay less interest, right? And then we shift towards paying off our debt payment, right? Or paying off our principal, right? This is kind of paying off the principal. Okay. How much do you have to pay in interest? We committed to paying 12%. That's per year. So each month I need to pay a 12th of 12%. Right? And so the amount of interest, uh-oh, I didn't give myself enough room. Can I do this? Interest on the first payment, right? I have to pay interest on the full $500, right? I haven't made any payments yet. This is my first payment, right? And so interest on the first payment is on the full loan amount, which is $500. So the amount of interest, right, if you want, I equals PRT. I guess that's kind of it works because it's just going to be for that one period of time, right? So let's use one that we know and love. Dust it off the shelf. The amount of interest I is going to be 500 times 0.12 and 1/12 of a year. We can use, like I said, we only use the simple interest formula because it's just for that one little stretch, right? No compoundings in between. Or you can take the amount owing, right, or the balance, and multiply it by the rate split over however many per year, payments per year we're doing. This becomes 0.12 divided by 12 is 0.01 or 1% times 500. We need to pay $5 in interest. The bank takes their $5 first.
Oh,
Yeah, because T's in years, yeah. Yeah, because the rate was an annual rate. Yeah, yeah, yeah. So the bank takes their $5. They really don't care. Then, but you've made a payment of $86.27, right? And so from this $86.27, they take their $5 and the rest is paying off your debt, right? And so now, how much is paying off your debt? Well, it should be probably 86.27 minus 5, which is 81.27. And these are all dollar amounts, of course, but so annoying. So now you can chip away $81.27 from that $500, right? Which means the balance here is going to be 500 minus 81.27, which is 500 minus 81.27. $418.73. Now you can do it again, but now, right, the change is that now you owe $418.73 instead of $500. And so now you're paying interest on $418.73, right? And so here, I'll try to make it as color coded as I can. $418.73 times, can I just do 0.01? Because 0.12 divided by 12 is 0.01. And so that's always going to be the case. I'm gonna have to round up to 19 cents, right? I get 4.1873, but the bank works in 2 decimal places, and so you'd have to round that up to 4.19. But from here, right? Notice the jump from $5 to 4.19, right? Just by paying off a little chunk. And so that's how mortgages work too, right? You want to pay off your principal, right? So that you can pay less interest. Now, out of your $86.27 payment, right, $419 is going towards interest, and then the remainder is paying off your debt, right? And so what do we expect? We expect it to be a little bit higher than 81.27, and so there's going to be this shift. So 86.27 minus 419, I get 82.08. And what am I chipping away at? Now I'm chipping away at 418.73 with this 8208. All right. And so 418.73 minus 8208. Now I owe $336.65. Maybe I should make this green. I don't know. Can match. Oh, maybe this should be orange. Just to indicate where it came from. Oh, but by that logic, this should be green. This should be blue. There, I think I did it. Cleaned it all up. Chain reaction. And then we can keep going, right? 336.65. Now that's the one that we're paying interest on. So if we multiply that by 0.01, we get times 0.01. Then let's see here. Make sure you round to 2 decimal places. There will be kind of discrepancy. We won't hit zero balance unless you never round it at any point, right? Then your balance should be zero at the end, but usually it's a little bit off, but not by a huge amount. So when I do my rounding here, I get 337. 86.27 minus 337. 82.90. Chip away at 336.65 minus that little guy. 253.75. Makes sense, right? We borrowed $500 and we're halfway through paying it off. And so I expect to kind of owe roughly half of it, 250. Right. We can keep going. Times 0.01 on to the next line. 2.54. 86.27 minus 2.54. Hmm. 253.75. Okay. Can see why we wouldn't want to do even a car loan, right? We'd have to do this for 60 rows. Yikes. It'd be some sort of soothing though, right? It's kind of working methodically through each of those 60 rows. You would have to pay a last 3 cents. Or if they're nice, they might waive it for you. They're not really famous for being nice. But there it is, right? And so kind of key takeaways, right? You're paying the same amount, right? But how much of it is paying off interest depends on the balance that you owe, right? And if you have less going towards interest, then more of your payment is going towards your debt repayment or paying off the principal, as we usually call it. And this is just due to rounding. This is from rounding our values. And now we've reached the end of the road for our financial math career, potentially. Or you can take Math 114 and do this all over again. What? But they take the whole term to do it? They level up a little bit more, but not a lot more. All right. Let you work on your homework problems. We're going to start chapter 7 on Thursday, which is on set theory. And yeah, if you have any questions, let me know, but I'll stop this recording. Otherwise, it's just me, I don't know, doing something on here. All right.